Chapter 2, How Computers Find Each Other on Networks. If you recall, at the end of last week, or during last week's lecture, we introduced our two network models. We introduced the OSI network model and the TCP/IP model, and talked about how they're broken out into layers. And why the layers? Because each layer provides a specific purpose in the overall communications process. This week, we're going to take this discussion a bit further. We're going to go in and examine some of the protocols that happen inside of specific layers. And we'll see that this is how computers actually find each other. Short answer, they find each other through addresses. But addresses that there are different kinds of addresses and they live on different layers. Now, for the point of our discussion, there are two network models. However, we're going to focus from here on out on the TCP/IP model and its 5 layers. So, addressing, what's going on there? Well, addresses, there are different types of addresses that both we humans use to refer to computers on networks, and that the computers use to refer to other computers. And they exist across a number of layers. At the very top, up here at the application layer, right, where our application protocols live, we do things like computer names, host names, and these are human readable names. Server 1, mail 2, that type of thing. And the reason why we have names like this is because the other layers, the other addresses that we use at the different layers, like IP addresses or MAC addresses, we'll get into those in a minute, aren't easy for humans. We don't do well with numbers, but we can do pretty well with names. And that's the whole point behind that. Moving through the stack, let's go to the internet layer. Right, layer 3, and this is the realm of the Internet Protocol, right? This is where networks are defined. Well, we have two kinds of addresses in there, IPv4 addresses and IPv6 addresses. Even though both are currently in use and currently valid, IPv4 is by far the more common of the two, and we're going to be focusing our discussions on IPv4, Internet Protocol version 4. We move even further down the stack, and we get down to the network interface layer, right? Layer 2. And this is referring to NICs. These are actual network cards, things I can put my hands on. Well, they have an address also called a MAC address, or Media Access Control address. And they're meant to individually identify computers, or identify individual computers. And we're going to go all into that and see how that actually works. The point here, though, is different layers using different forms of addresses. Now, you might have noticed I skipped over this transport layer stuff. What's going on with that? Well, at the transport layer, and the purpose of the transport layer is to determine the delivery type. Is it reliable delivery or unreliable delivery? We don't use addresses so much, but we use these things called port numbers. And the port numbers aren't so much to identify computers or networks, but to identify what service is being provided. We'll go more into that as we go through. So let's go all the way to the bottom, layer 2, right? And we have the MAC address. The MAC address is a 48-bit number, which means it's made up of 6 octets, octagon, octopus, 8, right? 6 times 8 equals 48. That is, in theory, supposed to be unique on the planet, meaning there's not supposed to ever be 2 identical MAC addresses. Well, in reality, that's not really the case. MAC addresses can be spoofed. We can change them using software. Sometimes manufacturing defects cause multiple MAC addresses. And, we'll see later on, that's not really a big deal. We can have multiple MAC addresses as long as they're not on the same network segment. But how do they get this? What's this thing about a 48-bit address that is globally unique? It's done this way. 48 bits, you cut it in half. So I have two 24-bit pieces. The first 24-bit pieces are known as the OUI, the Organizationally Unique Identifier. Right? This is assigned by IEEE, and it is assigned to individual companies. And if you're a manufacturer of network cards, like Intel, Microsoft, Dell, HP, Apple, whatever, you apply to IEEE, and you get an OUI assigned to you. That's for your company and your company only. Now, big companies like Apple, they have whole blocks of OUIs, but they're the only ones who are allowed to use those particular values. The second half of the MAC address, the last 24 bits, is just some identifier from the manufacturer, right? It could be sequential. It could be based on geography. Maybe we use one's based on made on the East Coast versus one's made on the West Coast. Whatever, it doesn't matter. It's the combination of the two OUIs, or the two halves of the MAC address, the OUI, and then that manufacturer-specific number that gives you a pretty unique number, right? And this system actually works pretty well. MAC addresses, and I did say they can be spoofed, and yes, they can be, but by definition, MAC addresses are meant to be permanent. And on this picture of a wireless NIC here, I mean, it's actually printed on the label on the side of the thing. Right, there's its MAC right there. It's burned into one of the chips on that little circuit board. Right? A MAC address is kind of like a tattoo. You tattoo your name on yourself somewhere on your arm, and that's not coming off. I could spoof it. I could cover it with a sticker, have another name on there, but ultimately my MAC address is permanent. Actually, we're going to skip ports and sockets for a moment because we need to talk about our layer 3 addresses. Let's go back up and look at our next layer. So if layer 2 is MAC addresses and those refer to individual NICs, layer 3, our internet layer, refers to networks, right? The addresses are provided by the Internet Protocol. We have two types. We talked about that, IPv4 versus IPv6. Why two versions? Why do you think that is? Because of this. IPv4, and this IPv4 has been around since the late 60s, early 70s. It's been here for quite a while. Is a 32-bit address. Whereas a MAC address was 6 octets, IPv4 addresses are 4 octets. 4 times 8 equals 32. So it's made up of four fields. Well, let me ask you this. How many possible values, how many IP addresses are there in a 32-bit number? Well, if you sit down and calculate it, a 32-bit binary number can represent 4 billion IP addresses. And that sounds like a lot. And back in the 60s, it really sounded like a lot. So nobody worried about it. In fact, we'll see also later that millions of these addresses were thrown away very inefficiently just to give us single addresses, things like our loopback addresses. Fast forward into time, even by the 1980s, late 1980s, it was becoming obvious that those 4 billion IP addresses might not be enough should this, at the time, the infant internet thing took off. 4 billion addresses. You know, at the time, that was enough for every man, woman, and child on the planet to have their own IP address. But what are you probably carrying in your pocket? Hey, a smartphone. In my case, it's an iPhone with an IP address, right? And a public IP address at that. So running out of IPv4 addresses was an actual concern. Cue IPv6. IPv6 was designed from the get-go to relieve the potential shortage of IP addresses. And compared to the 32-bit address of an IPv4 address, IPv6 gives us 128 bits. That's a lot of bits. If a 32-bit address represents 4 billion possible values, and every time I add a bit position it doubles, so 33 bits is 8 billion, 34 bits is 16 billion, and so forth, how many do I get if I keep doubling all the way to 128 bits? Well, don't try to do the math because it's a lot of it. The answer is 340 undecillion IP addresses. I wasn't even sure that was a real numbering value. I had to Google it. And it is. It's several orders of magnitude above the giga, tera, exa values that we're used to now. But it's a real value and a lot of IP addresses. Now, I did say that the focus of our course is on IPv4. How can that be? Weren't we running out of these addresses? Wasn't IPv6 designed to fix that? What's the deal? Indeed it was. A couple things. For one, IPv6, well, to be frank with you, is hard. Right? There's a lot to it. And it fundamentally changes how we do our layer 3 networking. Subnetting is completely different. It changes technology. Our routers require different techniques for dealing with them. So there's a lot going on there. There's a huge investment already in people's knowledge of IPv4. We've been studying this now for decades. So, and you're continuing the trend. We're still studying IPv4. Once you learn it, it's actually quite easy to work with, much more so than IPv6 anyway, in my opinion. And there have been some techniques developed over the last 20, 30 years to extend the life of IPv4. We'll take a look at a couple of those. So IPv4 addresses, the 32-bit address, we know that, 4 octets, and we know what it looks like, right? We've all seen the IP address 192.168.1.1. It's probably assigned to your home cable modem, right? That's an IP address. IP addresses are broken out into different classes, right? We have class A, B, C, D, and E. Now, really, the 3 that we care about, that we use every day, are class A, B, and C. The classes are defined by the first octet. So, if this, let's look at my IP addresses right here. All right, you can kind of see it. My 4 fields, and they're separated by periods. So, octet, period, octet, period, octet, and so forth. The class, and this is in terms, I'm going to caveat this, this is in terms of classful networking. In a future chapter, we'll talk about something called classless networking, which kind of changes this around a bit. But for right now, we're going to go classful. The first octet is what defines what class the network is in, right? So if my first octet is a value between 1 and 126, then this is a Class A network. Well, part of my IP address represents the network it's on, and part of my IP address represents that individual computer or that individual host. 32-bit number, and we look at our little picture right here. I have to have at least 1 octet representing my network, and I have to have at least 1 octet representing my host. Now, this is for classful networking. If you already know how to subnet, don't flame me. I get it. But for classful networking, this is what we're talking about. Well, for a Class A address, my first octet represents the network, and the last 3 octets represent the computers on that network. Well, because I'm only using 8 bits to represent network, I can only have really 126 possible networks. Why? Because I'm doing from 1 to 126, and I can't have a network number that starts with 0. 127 is a special case. We'll talk about that later. But because I have 24 bits, 3 octets representing the host, I can have up to 16 million computers or 16 million possible IP addresses on that network. Okay, let's look at a Class B. For a Class B, if my first octet is 128 to 191, I'm using the first 2 octets of the IP address to represent the network, and the last 2 octets to represent the host. I've got 16 bits doing each. As you can see, because I have more bits, I can have way more networks. But because I'm using 16 bits versus 24 bits of a Class A network to represent the host, now I can only have 65,000 assignable IPs on that network. So I'm trading, right? I'm trading host addresses for network addresses. Hold that thought. Let's go to Class C. If my first octet is from 192 all the way up through the 223 network, then by definition, I am a Class C network. I'm using 24 bits now to represent the network and only 8 bits to represent the host, the computers, or the number of possible IP addresses on that network. It's basically the opposite of what a Class A is. Now I've got 2 million networks to pick from. Cool. But each network can only hold 254 computers or 254 possible IP addresses. So what's up? Do we actually have networks with 16 million hosts on them? No, we don't. Right? This is kind of theoretical in that sense. The network traffic, the broadcast traffic alone would be such a roar on a network with that many hosts on it that communication would be impossible. Even Class B is 65,000, way over the top. The 254 of a Class C, though, is much more real world, right? And a Class C network is a very, very popular general purpose subnet to assign. I got a lot of them to pick from, 2 million different variants of my Class C network to pick from, and I could have 254 hosts in each one. That's getting pretty close to about as many hosts as I want on a network, right? I might want 500, and that's a subnetting task for a later job, but Class Cs are very, very common, and that's the network class you will most likely be working with. Now, some IP addresses are special purpose, right? For every network range, we have an address called the broadcast, right? And what is a broadcast? It means I'm talking to everybody. 255.255.255.255 means everybody. If I send that out, every host receives it. Remember back here, look, we went from 1 to 126 for Class A and 128 to 191 for Class B. What happened at 127? Technically, 127 is a Class A network, so it had 16 million usable IP addresses. However, the designers of the IP protocol, IP version 4 protocol, decided that we needed an address to refer to the computer itself. It's like looking in a mirror, right? And it's called a loopback address. So basically, they threw out the entire 127 network range and said, okay, 127.001 always refers to your own computer. Right? And that is indeed called a loopback. What happened to the rest of those addresses? Gone. There's no such thing as 127.002, 3, or so forth. That's kind of what I was getting at earlier, where when they started with 4 billion addresses, it seems silly that we'd never run out. So no one thought twice about throwing out 16 million addresses. Well, live and learn. Some IP ranges are private and some are public. And this is one of the technologies that extended the life of IPv4. Right? If all IPv4 addresses were public, meaning they're visible on the internet, we would be out of them right now and we would be studying IPv6. But for each of the classes, a range of addresses have been specified that are non-routable on the internet. Right? If I try to send any of these three classes of IPs out my default gateway, out my firewall into the internet, the first internet router will drop it. They're for private internal home use. For Class A, the entire 10-dot network is reserved. You'll never see that on a public address. For Class B, 172.16 all the way through the 172.31 network, private. And for Class C, 192.168 is reserved for private. And that's why I gave that example earlier. 192.168 is probably the most common network space for anyone's home and even small office use, right? Most cable modems, perimeter routers, whatnot, default to that when they're assigning out network space. If I get a private address that's non-routable on the internet, how does that, what happens? How do I access stuff? How is it that over here in my private network, let's say I'm using these Class A addresses, right, private, and on this computer, I want to go out on the internet. I open up Chrome. I want to go to shopping on Amazon or whatever. How does that work? Well, it's something called address translation, specifically network address translation or port address translation. Like everything else, we have a topic on this in upcoming weeks. But the Reader's Digest version is you have a device on your network called a gateway. Now, normally this is your firewall. And it's a layer 3 device. What does layer 3 do? At layer 3, we are joining networks together. Right? That's what Internet Protocol does. Divides and joins networks. Well, I got two networks here. Really. My private network inside my house, that's a 10-dot network, and a public network, probably through my ISP, through my cable modem, DSL modem, whatever. I can use private addresses inside. In fact, we're encouraged to. And here's a public address on my public interface of my gateway. So how does this work? Right? Basically what happens is if a person on here wants to open up a web browser, that packet, that data entity gets passed through my gateway, and as it heads out into the public internet, the source IP address, and we see next week where source and destination IP addresses fit into Internet Protocol packets, gets replaced with the public one. Goes off the internet, goes to the Amazon's web server. When the web server responds, it responds back to that public address. When it hits the gateway remembered that transaction, strips off the public address, puts my private address back on so it goes to my proper host within my own network. And back and forth and back and forth. Notice the one-to-many relationship. One public address being shared by many private addresses. And this is probably the biggest reason why IPv4 did not run out of addresses. Let's go up a notch. Let's go all the way to the application layer, layer 5, host names. What is that? These are character-based names, English words. Ideally, they can be numbers or whatever we want them to be, that refer to host. We also have these things called domain names, right? And in terms of the public internet, domain names refer to an organization. It refers to a company. It refers to whatever, even individuals, right? If I'm Acme Incorporated, I'm going to register Acme as a domain name so people can find my web server. The combination of the host name and the domain name is called a fully qualified domain name. FQDN. And this is what a URL is. That's how places on the internet are found. Now, there are suffixes to domain names. Think about it. www.yahoo.com, right? Yahoo is the domain name of the organization, in this case, the search engine, and then .com is the high-level domain name. There are only certain top-level domain names out there. Now, this list was recently expanded a few years ago, but it's still relatively small, right? Look, .com for commercial websites. We're all familiar with that one. .edu, that's what you use to even get to Blackboard. So schools get edu suffixes, government, and so forth. But we were talking about IP addresses, right? At layer 3, the internet layer, everything is all by IP address. Host names and domain names up there at layer 5 for us, for humans. How does that work? Well, an IP address gets translated back and forth to a domain name, and that's done by something called DNS, the domain name system. DNS is made up of a bunch of servers located all across the planet, and it's hierarchical, right? Meaning it starts at this one point up here, and it's like an upside-down tree, and it branches out. There are 13 root servers on the planet, 13 of them for the entire internet, that tell resolvers, which are clients, us, right, when we're out there looking for Amazon.com, where the .com DNS servers are, or the .org DNS servers. Then the .com DNS servers maintain the records, the host name and IP address records, for all the .com websites, like Amazon, Google, whatever. There's another DNS server for .edu that holds all the address information for websites that are educational, and so forth. And then finally, the authoritative DNS servers are actually owned by those companies or those organizations. So how does this work? Right? Here I am sitting on my client computer, and on every single computer, every time you're doing network communication, there's certain values you have assigned. The MAC address is burned into the system, but IP address, subnet mask, default gateway, all that kind of stuff. And one of the things we have is the IP address for a DNS server. In enterprise use, that DNS server is very likely internal to our infrastructure. For home use, that DNS server is probably being provided by your ISP. Either way, I'm sitting on my computer right here and I want to do some shopping. So I type in www.amazon.com, I hit enter. My system will go to my locally configured DNS server, right, from Time Warner, and it has to go find the IP address for www.amazon.com. First thing it has to do is find out the IP address for the .com servers. So this DNS server goes to one of the 13 root servers and says, "Hey, you know of any .com servers?" The root server responds back, "Yes, I do. They're at this IP address. Try that." The DNS server then goes to that server. "Hey, .com server, do you know the address for Amazon?" "Why, yes, I do. Its DNS server is this. Talk to him." And then this DNS server goes back out, our local one, goes out to the Amazon server. "Hey, do you know the IP address for www?" which is really the host name of their web server, and that's just the default host name that's been used for years. It's assumed if it's omitted. "Why, yes, I do. Here is the IP address for our web server." Once it gets that answer, the DNS server, our local DNS server, then provides that IP address to my client. And my client uses the IP address to get to the Amazon web server. Every time we do a piece of network communication, this happens, right? Or at least when we go to a different location on a network. What is a DNS server, really? Well, it's software, right? It's software running on some kind of hardware. Very often, it's an enterprise server class piece of hardware. But what about the software itself? Well, there's a couple choices on it. By far, the most popular one is one called Bind, which stands for Berkeley Internet Name Daemon or Name Domain. This is an open source product that runs primarily on Unix machines or Linux machines. Right? Very easy to configure and very, very common. Microsoft also has a DNS server built into its Windows Server. Right? It's part of Active Directory. In fact, Active Directory, the Windows directory service, requires DNS. If you're running Windows Server anyway, you have a DNS server internal to your environment, whether you want it or not. It has to be there. What's actually held inside a DNS server? Records. It is truly a database, right? All different kinds of records. I have A records that stores a host name to a IP address. I've got what's called pointer records, which maps an IP address to a host name. It's backwards. And then specialized records, things like MX records, mail exchanger records. These are used to specify email servers, along with others, right, for IPv4 or IPv6. So I've got all this set up. I got my DNS going. I'm trying to communicate, and I go to crack open my web browser, to click to go to Amazon to do some shopping, and I get the dreaded 404 error, address not found, location not found. Oh no, what do I do? How do I troubleshoot this? Well, I have some choices. If you're on a Windows system, or even on a Linux system, check the logs, right? The Windows Event Viewer is the Windows system log, along with its application logs and everything else. In there, if something's not working right, you will see an error. And there'll be a message over here telling you what your problem is. For example, in this case, a duplicate host name was detected on the network. You can't have the same host name on the same network. Or a duplicate IP addresses, or whatever. This log is very, very useful for diagnosing issues. I also have some tools that I can use. I'd mentioned earlier that, at layer 3, the internet layer, we have IPv4, IPv6. Well, there's another protocol that lives in there, which I omitted, and it's called ICMP, which is the Internet Control Messaging Protocol. This is a native layer 3 protocol whose function in life is to provide troubleshooting tools. Its most commonly used tool is called Ping. We're all familiar with this, right? Some say it's actually an acronym called Packet Internet Groper. I personally don't buy it, but it is what it is. And it's used to send a signal out to a host or an IP address out on a network somewhere that when the device gets it, it echoes it back. It sends it back like a radar ping, right? Ping! And if I get a reply back, I know that I have communication. It's not my network that's in the way. There's something else going on. I might ping by IP address, and just to see that if I have full network connectivity there. Right? Let's look at an example. If I got this little network going on here, and I want to see if this host can talk to this host, host A, host B, I might ping host A. Right? That packet will travel through. If it arrives here, this machine will respond to it and send a reply back. And that's how I know I did it. I might ping by IP address just to make sure that I actually have connection across my routers here. If that doesn't work, if I can't ping by IP address, I have a problem, right? There's something else going on with my network. Maybe a cable's unplugged or something, or maybe this router is down, or who knows. If I ping by host name, and it works, I know several things. I know I got DNS working because I had to go through a DNS server to resolve my host name to a IP address. And I know that my network is in good shape. What if I can ping by IP address but not by host name? Right? I ping 192.168.1.10 and I get a reply. I ping server 1, which is that machine's host name, and I get no reply. What does that tell me? It might tell me like something like my DNS is down, right? And I bring that up because by far, probably the most common reason for network problems is host name failure, right? DNS is actually a really big deal for us. Examples of what the ping command looks like, right? So I can ping by Google, or excuse me, ping by host name, ping by IP address, and so forth. Major operating systems, all the major operating systems I've ever seen have ping, right? Linux has it, Mac OS has it, Windows has it. It's a very valuable troubleshooting tool. What about my example? How do I know if my DNS servers are working properly? Well, I can test it. Also supported by most operating systems is a command called NSLOOKUP, right? Which queries my local DNS server, right? I want to know what the IP address is to server 1. So I would use the command. It's kind of hard to read right here. NSLOOKUP server 1. That'll send a request to my local DNS server. Hey, what's the IP address for server 1? If it's able to resolve it, it'll send it back to me. If it's not able to resolve it, it'll tell me that, and I know I've got some kind of DNS problem somewhere, either local to my environment or out in the greater internet somewhere. And that concludes our initial look at how computers can find each other on our networks. Many of these principles apply the same whether we're talking about our own internal LANs or wider area networks like WANs. For our purposes, we want to think about in terms of LANs, right? Local area networks. As a sysadmin, that's probably what we're going to be managing. If you have any questions, by all means, please feel free to contact me, and I will see you next week.